Okay, all right. Let's look at some solutions and answers to the workshop. All right, so the first question is about the snake. So the fangs of a snake can be modeled as hollow tubes with length L equals 2 centimeters and radius of 1 millimeter. And so that's an overall information that we can use for all the questions in the worksheet. But specifically for the first question, the venom is placed in a rheometer shown here in this diagram here, where the venom sits between the inner walls of the cylinder. So that's the yellow fluid there is the venom. So to keep the surface of the rotating cylinder moving at a speed v relative to the container wall, a continuous force F is applied tangentially to the rim. So that's the force shown in blue arrow and velocity upwards, tangential to the force. So by measuring force to v, what property of the venom does the rheometer measure? So what do you think it's being measured by the rheometer? So so Hannah says it's the viscosity. Yeah, that's right, because viscosity relates force. So the equation we've seen earlier, the mathematical representation of viscosity relates the force to the speed of fluid flow. So even if the area and the length are not given, so the fact that the speed of the how fast the venom flows as you rotate the rheometer depends on force, means that the rheometer should measure the viscosity. Okay, and then for the second question, for a given cylinder wall V, more force must be constantly applied to rotate the cylinder when venom is the fluid between the walls compared to when water is used. So what can you say about venom and water? Which one is more viscous, the venom or the water? Venom, right? Yeah, so the more viscous the fluid is, the more force you need in order to make that fluid move. That's of course given by our equation here, that the speed is proportional to the force, and the bigger the viscosity, the bigger the force you need. Force applied tangentially, so the rotation of, let me just see if my pen. So this cross section of this top view, this is the picture on the right, that's the top view of the rheometer. So the rheometer is being rotated anti-clockwise, shown by this red arrow. So this red anti-clockwise arrow. So tangential means you take a point along that circular path and just draw a straight line. Yeah, so that's tangent to that point. So at that point, that's the force here. So if that's your circular path, if you take different points, so tangent means you're drawing a straight line that's just grazing the point that you're looking at. So that's tangent. At this point, the tangent force. Okay, so it's as if you're drawing a straight line. So instead of looking at this circular rotation, you're getting one point and drawing a straight line relative to that. Why is it upwards? Because your rotation is anti-clockwise. So at this point, your tangential force will be downwards because your tangential force should follow this anticlockwise rotation. Does that make sense, Hannah? Yeah. Okay. And so the next question, assuming venum is a Newtonian fluid, meaning the viscosity does not change as the rheometer rotates, as you apply stress, the viscosity remains the same. How would the force change if you wanted to double the speed? So if the speed was doubled, how should the force change? Should it double or halve? Right. I guess the essence of this question is like if you wanted the venum to move 2 times faster, okay, the speed is doubled. If you wanted the venum to move 2 times faster, how should you change the force being applied to the rheometer? Will you double the force or will you have the force? Right. Okay. So yeah, so the speed would be doubled if the force is doubled. Yeah. So I can see there in the chat box some correct answers. If you push with twice as much force, then the speed, yeah, then the speed will also move with twice as fast speed. And we can see that from this direct proportionality between force and speed, but you can also think about it intuitively. Yeah, that's okay, Oksana. I figured that you meant force, so that's okay. So the force should be doubled if you want the speed to be doubled. Right. Good. Okay, so conceptual questions for the first part. Now for the second part, you have here the snake bites a prey. So when biting, the snake only has about 100 milliseconds. So of course, milliseconds, that's a measure of time to inject enough venom to stun its prey. And to maximize the volume delivered in this time, what should an individual have to have the biggest advantage? Okay, so which means which factor between pressure, radius, length, or viscosity would give the snake the ability to inject more venom over this same amount of time, 100 milliseconds. Should the pressure in the venom duct be twice that of a regular snake? Should the radius be twice that of a regular snake? The length, should it be twice? Or should the viscosity be half that of a regular snake? In short, which variable affects the amount or the flow rate the most in a viscous fluid? Right, so viscosity, yes, viscosity will affect the amount of venom injected. We know that the more viscous it is, the less volume, less venom will be injected given everything is the same. Yep, good. So we should look at Poiseuille's equation because Poiseuille's equation relates the effect of different variables to the amount of venom injected. Yeah, so the amount of venom injected comes into the flow rate. Okay, flow rate is defined by the amount or the volume of venom injected over that 100 milliseconds. And for a viscous fluid, the flow rate is affected by different variables given by Poiseuille's equation. So you're right, Hannah, we should look at Poiseuille's equation. So here we can see pressure difference. Pressure difference is directly proportional to the flow rate. Okay, so if the pressure is twice that of the regular snake, okay, pressure difference, yeah, So yeah, so to maximize the volume, we have to maximize the flow rate Q. Let's look at the pressure difference. Okay, twice. So the first choice, the pressure difference is doubled. It's twice that of the regular snake. Double the pressure difference means double the flow rate, right? So the pressure difference, the flow rate Q is directly proportional to the pressure difference, which means if you double the pressure difference, you double the flow rate. Okay, the second choice, the radius of its fangs was twice that of a regular snake. So radius is this R there. Okay, so if you double the radius, okay, because the radius of the snake is twice that of the regular snake. So you double the radius. Notice how the radius is raised to the power of 4. Okay. So double the radius to R, but you have to raise the radius to the power of 4. Okay, so that means 16 times R raised to the power of 4. Good. So double the radius because of this exponent of 4, the flow rate will increase by 16 times. Okay. Right. Okay, the third one, notice, of course, that the flow rate is directly proportional to the radius as well. So if the radius increases by 16 times the original radius, then the flow rate should also increase 16 times compared to the original flow rate. Does that make sense? Why it's 16 times? Yep. Good. All right. The third choice, the length of its fangs should be twice that of the regular snake. So if you double the length, notice how the length is down here. It's inversely proportional with the flow rate. So if you double the length, it's essentially just multiplying, putting 2 below the denominator, and that has an effective effect of halving the flow rate. Yeah. So double the length means half the flow rate, and similarly for the viscosity, the last choice. Okay, if you have the viscosity, just erase that one. So if you have the viscosity, it's inversely proportional to the flow rate. So half viscosity means twice flow rate. So looking at what we've worked out here, you can increase the volume. You can increase the volume by increasing the flow rate, and the radius will have the biggest effect in the volume, and therefore the flow rate. So smaller flow rate means it minimizes volume, because flow rate is the amount. So it's the other way around, Hannah. So flow rate means amount delivered divided by time, or volume delivered divided by time. So the smaller the flow rate, that means you're delivering less volume. If you think about it, smaller flow rate means that your fluid is flowing slower. Okay? Because flow rate is also equal to area times the speed of the fluid. So if you have a small flow rate, your fluid is moving very slowly, and so it's delivering a small amount of fluid for a particular given time, as opposed to when you have a high flow rate, then your fluid is moving fast, and so the delivery is faster, and so you're putting in more volume over a certain amount of time. Yeah, so you're right. So you're right. So the venom should be injected quicker. So venom should be injected quicker in order to maximize the volume of venom delivered by by the snake, and quicker, quicker means higher flow rate. Yeah, so I think so in 4, it's the viscosity that is half. So in 4, it's the viscosity that's half. It's not the flow rate that is halved. So if you have the viscosity, so you'll have there the whole thing pi r4 p1 minus p2 divided by 8L, but you have the viscosity. So instead of, for example, instead of having a viscosity of 2, you have a viscosity of 1. So you're dividing this whole thing with a smaller number. If you have the viscosity, you're dividing everything on top with a smaller number, right? And therefore, smaller viscosity will give you a bigger flow rate. And a bigger flow rate will give you a bigger volume being delivered, right? Which makes sense, because if you have the viscosity, that means that the fluid is thinner. Yep. Oh, 2 times. Yeah, 2 times eta. Oh, I'm sorry. Yep, you're right. Sorry. Yeah, good catch. So yeah, I should put 1/2 because that's what's being. So it says there half, viscosity is half. So I should put half times viscosity means twice the flow rate. Yeah. Yeah. Good. Good. Right. So yeah. So yeah. So yeah. I think we agree in the end. But looking here at the effect of the parameters on the flow rates, you can see that the radius gives you the biggest effect. So the radius, by changing the radius, the amount of venom delivered increases dramatically because of this exponent 4. Okay. Okay, good. Right. Okay, next question. So by contracting powerful muscles, a snake is able to increase the gauge pressure in the venom by 600, by this much, 6,660 pascals, and the flow of the venom through the snake's fang has a Reynolds number of 21. So, so the first question, we have 2 diagrams here. Which of these 2 diagrams depicts the flow of the venom? Is it the top one, or so the red lines show you the streamlines of the fluid flow? Yeah, the top one is laminar flow, right? Laminar flow. And this is the bottom one is turbulent flow. The Reynolds number is 21. It's less than 3,000. Therefore, that will be laminar flow. And so, yeah, so, sorry, less than 2,000 for laminar flow. And so the top one should be the correct answer there. And the streamlines, the arrows depict the streamlines or the path of the fluid as it flows. Good. Good. All right. So so is that, so the next question asks us to find the velocity at which the venom flows through the fangs when injecting into a lizard which has a blood pressure given here. Right. So So you have there a pressure difference. So let me just write down here. The pressure in the fang from the previous slide is 6,660 pascals. And so the pressure in the snake's fang is different to the blood pressure of the lizard. So there's a pressure difference there. And it's that pressure difference that will cause the venom to flow, because venom is viscous, and this is the viscosity of the venom given here. Okay, so writing down everything we know. The pressure of the fang, the pressure of the lizard is given in millimeters of mercury. Okay, be careful with units here. Since the pressure of the fang is given in pascals, and that's the base or basic or SI unit, you have to convert millimeters of mercury to pascals. And the conversion factor from lecture 12 is 1 millimeter of mercury is 133 pascals. So we use that conversion factor to convert to pascals. The radius of the fang was given as before, and the length was also given. The viscosity, again, be careful with such prefixes. Milli, of course, means 10 to the minus 3. So keep an eye out for those tricky prefixes, and convert the units accordingly. Okay, so we know Poiseuille's equation gives us the flow rate for viscous fluids. Okay, there's no sense using Bernoulli's equation here because there's no height difference that's given. But in fact, what we're given is the pressure difference. What we can find is the pressure difference between the fang and the lizard. So Poiseuille's equation will be the sensible equation here, where P1 minus P2 is the pressure difference, and we want to find the velocity. Okay, Poiseuille's equation doesn't tell you directly anything about velocity, but we know that Q is equal to velocity, right? Q, flow rate, is equal to area times velocity. Okay, but by using Poiseuille's equation, we can solve for Q, and then after that, we can solve for speed V. Right, so we know everything, just substituting everything, the radius, P1 minus P2, 8 times the viscosity times the length, we can solve for Q. Right? Good, and then once you know the flow rate from Poiseuille's equation, you can now use the general definition for flow rate to find the speed. Q is equal to AV. A, of course, is the cross-sectional area of the fang through which the venom is delivered. We can assume, you can always assume to be cylinder, so that the cross-sectional area would be a circle. So unless otherwise stated, unless we specifically state that the cross-sectional area is a rectangle or a square, for example, you can safely assume that you can model the pipe as a cylinder, and therefore the cross-sectional area will be a circle whose area is pi r squared. Okay, so therefore the velocity after rearranging Q equals AV will be the flow rate, which you obtain from Poiseuille's equation, divided by the area pi times the radius. And then don't forget there's a square. All right, and that should give you a velocity, or just speed of 0.5 meters per second. Right? Okay, are we happy with the solution for this question? Yep. Okay. All right. So the last question, I think, is to find the density of the venom. Okay, so looking at all our equations for viscous fluids, the density only comes into the Reynolds equation, Reynolds number equation, where density is this rho. Of course, density also comes into Bernoulli's equation, but again, we don't have information about the heights or the elevations, and so Bernoulli's equation would be useless in this case. So Reynolds equation from before, the Reynolds number for the venum as it flows down the fan was given to be 21 in the previous question, where we were asked whether it was laminar or turbulent flow. The A area is the cross-sectional area of the fan through which the venum flows through as it's being delivered. We said that the cross-sectional area is a circle, and we can solve that because the radius is given, 0.001 meters for the radius. What else we need? So the area can be solved. We need the viscosity of the venum, which was already given in the previous information. Again, remember to put the times 10 to the minus 3 to represent the milli in the unit of given viscosity. And then the D is diameter. Okay, the radius is given, but we know the diameter is just twice the radius if our cross section is circular. So it's twice the radius, therefore diameter is 0.002 meters. So the only thing we need is the flow rates. Okay, Q, flow rate, which is the area times the speed. Right, so you have there the cross-sectional area of the fan times the speed of fluid flow. So we essentially have everything we need except for what's being asked, which is the density. Right, so to find the density, we have to rearrange the Reynolds number equation. So density is up here. It's being multiplied with dq, so we need to divide. Maybe I'll do it so it's not so much cluttered. I'll do it here. So we need to divide both sides by d times q. Okay, divide dq to get rid of dq, and then to get rid of a times eta, we have to multiply with a times eta both sides, and that gets rid of a times eta. Okay. And then so your rearranged equation for density is the Reynolds number times the area times the viscosity divided by the diameter times the flow rate. And we know everything, so it's just a matter of plugging in the numbers. Yeah, just checking that I have the numbers correct. Yeah. Okay, and carrying out the calculation. So can we do, so there's a question here, can we do rho equals dq over Reynolds a times eta? So that will be the dq yeah, so that's flipped, that's the flipped rearranged part. So you cannot, so the quick answer to that is no, you cannot do dq, you cannot do rho is equal to dq times Reynolds number times A times eta, because then it will be a different equation. So notice here in the rearranging that dq is on top. So in the original equation here, rho dq over A times eta. So to get rid of dq, dq is tied to density via a multiplication sign. Right? So to get rid of dq, you have to do the reverse operation of multiplication, which is a division. Right? And that automatically then, so you have to divide with dq to get rid of dq on the right side, but you also have to divide the left side with dq. So that automatically puts dq below the Reynolds number, RE. Right? And then A times N, so A times N is being tied to the density rho via this division. So notice how density is divided by A times eta. And so to get rid of A times eta, we need to do the reverse operation of this division. The reverse of a division is a multiplication. And therefore, we have to multiply the right-hand side of the equation with A times eta. Okay. Right. And therefore, we also have to multiply the left-hand side with A times eta. So by doing that rearranging, so Reynolds number will be together with A times eta, as you have written down there, but it should be on top of the denominator sign. And then dq should be below the denominator sign. Yeah, okay, good. Right. Okay, so that's the density that we obtained, 1050 kilograms per cubic meter. Yeah. So I think that's all the questions for those are, yeah, let me just check the worksheet. Yeah, so we've answered all the questions in the worksheet. So unless you have any other questions, of course, you're free to ask any question, even if it's not in the worksheet, maybe the lecture or other questions at all. Right, so I don't see any questions in the chat box, so then we can perhaps end this session. Yeah, the review workshop, I'll just do that online because nobody's really turning up in the face-to-face classroom. But if you do want to ask something during the review session, I don't have any plan of what specific thing to discuss there, so it's really just drop-in sessions with your questions. But I will be online at 1 o'clock for that if you want to join in. Otherwise, thanks everyone. Have a good weekend. The recordings will of course be on stream, but have a good weekend and I'll see you again next week.